Hey there. All right, we are in Lesson 12, Unit 5. Today we are going to learn how to describe the effect of changing A and B on a graph that represents the exponential function A times B to the x. So what happens when we change A and B. Also, we're going to learn how to use equations and graphs to compare exponential functions. And diving right in. So, spending gift money. Jada receives a gift of $180. In the first week, she spent a third of the gift money. She continues spending a third of what is left each week thereafter. Which equation best represents the amount of gift money, G, in dollars she has after T weeks? Be prepared to explain your reasoning. Okay, so she continues spending a third, which represents the amount of gift money she has left after T weeks. So she's spending a third. She has left 2/3. Okay? A lot of you I see, at least in your last quiz, are going for something like this, 180 minus 1/3 T. That only works for the first week. Okay, that doesn't work for any week after that. Okay? Graph or equation number 2 represents the amount you're losing each week, not the amount you have left. And this one, I don't even know what that one's doing, okay? That means I have an initial value of a third and I'm increasing by 180 each week. No. Here, my initial value is 180 and the amount of money I have left in my pocket each week is 2/3 of that. All right, so number 4, if we look, I have G equals my initial amount times the amount remaining, if I could spell, remain, there should be an M, raised to some value, in this case T. Okay, so those are the graphs that we're looking for. We have initial amount times the remaining amount, the amount remaining, raised to the T. And it was reported to us in how much she loses each week. So we want to use the equation with how much she has left. Each of the following functions, f, g, and h, represents the amount of money in a bank account in dollars as a function of time, x, in years. They are each written in the form m of x equals a times b to the x, where here I have the initial amount and my either growth or decay factor, all right? So let's see what we're doing here. F of x, my initial amount is 50. It looks like I'm doubling each time period, each year. Here I have an initial amount of 50 and I'm tripling each year. Here I have an amount of 50 and my growth factor is 1.5, which is equal to 3/2 each year. And here I have an initial amount of 50 and it looks like I'm decaying or I'm getting smaller by 1/2 each year. All right, so use graphing technology to graph each function on the same coordinate plane. Explain how changing the value of B changes the graph. Okay, hold on. So here A is the same in each one of them. All right, so what we see here, I've graphed them all. F of x, g of x, h of x, and j of x. They each have an initial value of 50, which is good because right here we see the vertical intercept at 50. Okay, that's my initial amount. If I look at the red one, I'm doubling each time period. So if my initial value is 50, red means at one time period of 1 year, I'm going to have 100. At time period of 2 years, I'm going to have 200, right? G of x, I'm tripling each year. So that's the blue one. At time period of 1 year, I have 150. And then I can't see the time period of 2 years because it would be 300. No, 150, tripling, big. Okay, it's early. And then h of x, I have my initial value of 50 and it's times 1.5. So my growth is going to be slower. You see that one is the lowest graph. It's the least of the three that are growing. Blue is growing at a faster rate because the growth factor is the biggest. Red is growing at a medium rate because the growth factor is in between 3 and 1.5. And 1.5 or 3/2 is growing the slowest, right? And then we have J of X, which is decaying or not growing. So we still have our initial value of 50, but in each time period, it's getting cut in half. So here's 25, 12.5, etc. I can click on this. Yep, so after 1 year, it's cut in half. After 2 years, it's cut in half again. Okay, and then it's going to keep on decaying as it approaches 0. It will never touch 0. It always gets smaller and smaller and smaller. All right, what are the questions we had here? Use graphing technology, check. Explain how changing the value of B changes the graph. And we did. Growing fastest, growing the mediumest, that was awesome. And growing at the slowest. And then here we have our decay. All right, so now let's change our equations to P, Q, and R. So we're going to keep the growth factor the same for each of these. All going to be 4. And then we don't need J of X. But we're changing A, so our initial value is going to be changing. Okay, for P of X, our initial value is 10. And then for Q of X, our initial value is 40. So what's that going to do? Our initial value is 40, so that's our vertical intercept. For time equals 0, you have 40 of whatever we're talking about. And then R of X, our initial value is 100. Okay, so we're growing at the same rate. Our growth factor is the same, but our initial value is different. Okay, the smallest initial value is P of X, which is red. Q of X has an initial value of 40, and R of X has an initial value of 100. So R of X is always going to be the largest function. Okay, it's always going to have the largest value. It's always going to be greater than the other two because we start at a higher amount with the same growth factor. Okay, Q of X is always going to be in the middle, in between green and red, because it starts out with the middle value and it has the same growth factor. And red is never going to surpass blue or green because it starts with the smallest amount and it has the same growth factor. Okay, so my changing value of A shifts the graph up. Okay, it shifts it up or down depending on the initial value. Cool. All right, let's go back to here. All right, are you ready for more? Are you ready? Lesson 12. Lost an eye. All right, so graphs representing exponential decay. Match each equation with a graph. So they each have the same initial value. 1/4 is the smallest growth factor, and this is the amount remaining, okay? 1/2 is the next biggest growth factor, so it's the next most remaining. Here is the next biggest, so the next most remaining, and this one has the most remaining. Okay, so here not much is remaining at each time period. So I believe this is going to be D. And then the next one we've got C. And then here B. And then here we have A. Okay, the larger the growth factor, okay, that's the most of the amount most initial amount remaining. Make sure I'm hitting everything. This is 0.3. All right, so yeah, there we go. DCBA. We saw over here in our graph, I should have kept those. Let's just keep all these 10. So we want the same initial amount. Okay, so only 1/4 of your initial amount remains. So you're losing more of it. You're losing 3/4. You have 1/4 remaining. Doing great. Too many parentheses. Okay. Here you're losing half. You have half remaining. So you have more of your initial whatever it is. And then let's do the most remaining. So you're only losing that last equation. You're losing a half of your initial, or a fourth of your initial amount. You have 3/4 remaining. Okay, so that is your difference. With red, this is the amount remaining. You're losing 3/4. You have 1/4 left. If you're talking about $100 of gift money that you spend 3/4 of it every time, that means that you don't have much left in your pocket. Here, gift money, you spend half of it at a store every week. You have half remaining in your pocket every week. Here, you spend a fourth. You have 3/4 remaining. Okay, so that's what happens when you change B. Let's see what else is on this page. Functions f and g are defined by these two equations. Our initial amount times 1/10 of it remaining each time period, and $1,000 initial, or sorry, 1,000 initial value, and 9/10 remaining, losing 1/10 each time period. Which function is decaying more quickly? Explain your reasoning. So this is the smallest fraction, so it's decaying more quickly. F of x is decaying more quickly because we've got 1/10 remaining each time period. Losing 9/10. Okay, we have a very small amount remaining of the initial value each time period, losing 9/10, which is a lot. G of x, I have 9/10 remaining. 1/10 lost. Okay, 1/10 is not very much. And then use graphing technology to verify your response. Let's go for it. This was f of x. 1/10. And then it was g of x, wasn't it? And we can't see the 1,000. Okay. F of x is decaying much, much faster. Yeah, that's the problem. Okay, f of x is the 1/10, decaying much faster than g of x. All right, I would look over the lesson summary before you quit for the day. Great thing to study before an assessment too. All right, good job today.